That was the equalizer. Now I'd like to talk about some co-constructions, some dual constructions. Hmm? And just because it's on our mind, I'd like to now talk about the coequalizer, if we could. Okay, so you've seen the equalizer. The equalizer had, well, how does this picture differ from the equalizer? What did the equalizer have? It had objects X, object Y, and morphisms. Oh, yes, going between them. But what did we have there? We had object capital E with a morphism. What?
Into X.
Into X. This one we have morphism Q coming out of Y. Hmm? And there's what we're showing here is the basic shape, basic structure of the coequalizer, but it has to again admit to it has to offer a certain universal property. It has to be the best, the most quintessential of them. So any other object that has this structure in the category, so it has a Q that has this sort of pattern, has to uniquely be factorized by this capital Q. So if there's a Q prime, there's a unique, if Q is the coequalizer, it has to have unique morphism to any other Q prime that has this property that, oh gosh, right. That I should have had the property. So it has to be that, can you guess what the property is here? What after what? It's yeah, so it's hidden here. Exactly. So okay, so now I've bungled this up by putting too much stuff on the same. There it is. So Q after F must equal to Q after G. Hmm? Okay, so Q is automatically, do you remember E was automatically a monomorphism? Do you remember that? Q is automatically an epimorphism. It's the dual out of a monomorphism. Okay, now the coequalizer might take a little bit of extra time to get your head around, and I want to talk about it. It's actually an extraordinarily useful, almost, I mean, it's really a delightful little gadget, a delightful little construction, but it requires a bit of thinking. On the other hand, once you get it, you'll recognize that it's really, really useful in many, many places. So I'm going to take this off the board. I got some pictures of it. And I'd like to do something similar for the coequalizer. And if I had presence of mind, I would have done it over here. That's what I should have done. Oh well. Okay. So here's our X. A, B, C. And let's turn this off. Okay. And here's our 0, 1. And once again, we have two morphisms, two functions. Oh, so we're considering this in set, I should say. Well, let's consider this in set right now. So let's develop an intuition for it in set. It's a bit of a more fancy instrument. So I'm going to or more involved to think about, so I'm gonna consider it the same. Okay, so here's our F, and now we want to have a G. And I'm going to have G map A to 1, and I'm going to have it map B to 0, and C also to 1. Okay. Okay, that won't be quite as interesting, so I'm gonna map C. There we go. Okay. This is a fun thing. And now we're going to have another set, which is going to be called Q. And we might call this co-equalizer of F and G. And there's going to be some function from, this is X, this is Y, this is Q. There's going to be some function here from Y to Q. Do you remember what sort of function it is? Well, do you remember what it was when we had E? What was it? Okay. Injective function, because it corresponded to a monomorphism, to a morphism that was monic. Here we have a morphism that's an epimorphism. Now, epimorphisms are not identical to something that we call surjective, but they are related to. There's actually something called a split epimorphism that's more directly related to it. But here it's going to go to some full set of things. Okay. And what we're going to do is we're going to consider equivalence classes of Y. We're going to consider, so notice, this is not going to be a subset of X. Remember before E was a subset of X? This is actually going to refer to things in Y. But it's not going to be just the elements of Y. This is a really important point. It's going to be equivalence classes of elements of Y. Things in Y that are glommed, that sort of include, that they're going to be sort of subsets of Y that have been made equivalent to one another by virtue of the mappings by F and G. And specifically, I want to look at that criteria here to draw your attention to this. You'll notice this. Q is a set representing the equivalence classes of Y, not of X, Y, where two values of Y are considered in the same equivalence class. If there's a value of X such that F of X equals, okay, wait a minute. Value of X such that F of X equals G of X. Okay. That's actually no, that's actually that these two will be considered. It's actually, that's not a correct statement. So in other words, for a given value of X, F of X and G of X are considered in the same equivalence class. So F of X, where so F of X and G of X are considered in the same equivalence class of Y. So in other words, let's walk this through here with our example. So here, let's consider a given X value of set A. Call it lowercase. What does F map X to? So what does F map X?
F of X.
So it maps it to F of X. What is F of X here? What is F map A to?
0.
0. So X is A. X is A. Okay. And what does G map it to?
1.
1. So we're going to consider 0 and 1 now to be in the same equivalence class. So actually, I had switched this around. I could have actually kept it. I said it wouldn't be interesting. It is interesting. So 0 and 1 will consider the same equivalence class. What is F map B to?
0.
What is G map B to?
Also 0.
Okay, so 0 and 0 are in the same equivalence class. Okay. What is C map? What is F map C to?
1.
What is G map C to?
Also 1.
Also 1. So 1 is in the same equivalence class. So we know 0 is in the same equivalence class as itself. 1 is in the same equivalence class of itself. No added information. But 0 and 1 are in the same equivalence class. So there's exactly here one equivalence class in Q, which has 0 and 1 in it from this. And this here is, what do we call it? Lowercase q? Is that what it was called, lowercase q? This is the single equivalence class. It's the equivalence class of this dictated by what we're mapping elements of this onto. Let's do a more interesting example. We're going to have A, B, C, D, and we're going to, sorry, A, B, C, and we're going to have 0, 1, 2, 3. And we're going to have our Q here. Okay, so let's suppose we have A mapped to 0, B mapped to 2, and C mapped to 3. Well, this will be okay. I was going to do sort of, but this is actually a nice textured one. Okay, so let's suppose we say that G maps A to 1, maps B also to 2, and it maps C to 2. Okay, so we're going to continue. We're going to consider as the same, as being in the same equivalence class, any things that are the same, any things in Y that a given element of X is mapped to by F and then Y and then G. So 0 and 1 are considered in the same equivalence class because F maps A to 0, G maps A to 1. So we'll start building up our equivalence classes here. We'll see how many there are, but I'm going to have one equivalence class which has at least 0 and 1 in it. Possibly I should have left more room. Okay, now there's another equivalence class with B. Well, okay, so B can identify things. B can glue things together, right? We're going to glue together anything mapped to by a given element here. 0 and 1 are glued together. B is mapped by F to what? Mapped by G to what? 2. So it's glued to itself. Nothing, no nothing information added. C is mapped by F to what? And it's mapped by it's mapped by G to what? 3. So what do we glue together? 2 and 3. This is our equivalence. This is our set of equivalence classes. It has 2 elements in it. I'm suggestively calling it 0, 1 and 2, 3. And tell me the mapping of this. What does this mapping consist of? Q here. Can you give me the mapping?
0 maps to the top.
0 maps to this. 1 maps to what? 2 maps to
The bottom.
like that. This is Q. Is this a surjection? Remember the definition of a surjection? It has to map onto all of these. Does it map onto all of these? Yeah. Does this map onto all of these? Yeah.
You want to have a counter example, right?
Okay, so I'm not done yet. Let's suppose we have A, B, C and 0, 1 and F and G are the same. Maybe I'll do it like this. F and G are the same here. They completely coincide here.
He was just going to leave the set of equivalence classes of each individual element of Y.
Yeah. So how many things will this have?
2.
2. 1 for each of these. Because there's nothing glued together differently. A and F and G map A to the same thing. So it's glued to itself. 0 is glued to itself. B is mapped by F and G to the same thing. So that's glued to itself. 0 is glued to itself. So C is mapped by F to 1 and G to 1. So 1 is glued to itself. So this set is always just going to be what? Just what? That's all it is. Which here is what? So this is going to be the co-equalizer of F with itself. What if F, what's that?
I was going to say, so it's like the last few equivalence classes, just like the netting, the netting that the arrows between X and Y creates. So it's like if you're
That's right.
travel back and forth with it, what's as far as breadth you have.
There's like a net here. So you'll notice that like 2 and 3 got, this is an important point, Jeff. That's actually a very useful way to think about it. Like 2 and 3 got identified here. Why? Well, so it's kind of a net that there's kind of this graph that linked them up, right? There's a graph. There's a graph here. Oh, I should have turned off this.
Kind of reminds me of the.
Like maybe you could get the. Sorry, Jeff.
Yeah, it reminds me of the participants in Happy View 2.0 with the screenshots that
Yes.
the multiple screenshots.
Yes, exactly. I bet there's a co-equalizer there somewhere. Actually, seriously, we should think about that. So 2 and 3 got identified here because a given thing here was mapped by f to one versus the other function to the other. And so they got glommed together by virtue of that. 0 and 1 here, it's the same thing. They got glommed together because a given element in X got mapped to the two of them, right? Now, this is something which can get quite interesting, though. If we have, and I'm going to test my height here. Let's suppose that we have this. So we have what really matters here is yes, that will do it. That's gonna do it. That's gonna do it. Okay. In fact, we don't even need C. Let's get rid of, let's simplify it. Okay. Okay. We're gonna have A mapped to 2 here. Doing an injustice. It's online. Okay, so A is mapped by F to 1. A is mapped by G to 2. B is mapped by F to 2. And B is mapped by G to 3. Okay, what does Q look like here? How many equivalence classes are there? Using the
One,
class and
1, 2, and 2, 3 overlapping is 2.
sorry?
1, 2, and 2, 3 overlapping is 2. Is that correct?
It's the full thing.
It's the full.
Because you can picture it like traveling back and forth.
So-
you can
so
get from
the-
3 to 1 somehow.
That's
through
right. These
that.
two, these are sort of all in one connected component. So this is the intriguing thing. This is all one component because 1 and 2 are identified because of this. They're in the same equivalence class. Ujay was getting it. 2 and 3 are identified because of B. They're in the same equivalence class. But because of that, it follows that 1 and 3 have to be in the same equivalence class. Even though there's no particular element in X that is mapped by F to 1 and mapped by G to 3. Like there's no C that's mapped by F to 1 and G to 3. It follows that 1 and 3 have to be in the same equivalence class because 1 and 2 are in the same equivalence class, 2 and 3 are in the same equivalence class, and therefore, by extension, 1, 2, and 3 are all in the same equivalence class. And here, all of these go on to this one equivalence class.
So if, for example, you thought maybe A and B were 2 separate participants in the study, A submitted screenshots 1 and 2, B submitted both 2 and 3.
Yes.
You'd have to consider that
That's right.
A and B are the same person.
A and B are the same person. That's right. That's exactly right. That's right. Yes. Beautiful example. So here we have, and you can view this as an emergent property of sorts, in the sense that there's no one thing that links up 1 and 3, but it emerges from this network of connections. And Jeff put his finger bang onto it by saying that there's kind of this web of this net. It's almost like these are in the same graph. They're in a connected graph together. Because, like these two overlap with this graph. So you can think of this as kind of like one graph, this graph, and there's this overlap here. Therefore, they're all implicated in this common connected component, 1, 2, and 3. That's it. So this is the coequalizer. And the coequalizer is incredibly powerful. I will note that if you take, this is a bit of an aside, but it is mentioned in the book, and I think I'll mention it. You remember the category, the schema category for graphs, right? Like this. Remember that? Source target. And if we consider a given map from this to set, a given instance of this schema, a given preview, right? Call it X. We consider if X of E, and that's a set. Object maps to a set. X of E, that's some set. And we consider X of S. What is that? That's what is this? It's a function mapping the set for each edge in this set it to a particular vertex. That's a source vertex. We do the same thing with this, right? Right? The coequalizer of those functions you know what it is? It's a set of equivalence classes of V of these vertices, kind of clumping together vertices that with their a given vertex is clumped together with things so any vertices that are separated by an edge are clumped together, right? So a vertex it's kind of like this. A given edge here might go to vertex 1 through source, and it might go to vertex 3, so vertex 2 via source, vertex 3 via target, and therefore source and therefore 2 and 3 are considered in the same equivalence class. So what this picks out is the connected components of the graph. All the things that are connected by one or more edges to each other are grouped into a single component. A single component of the graph are grouped together. Because, and again, it gets to this emergent nature. No one edge may directly connect 1 and 3, but because they're implicated, they're connected by virtue of one other edges that are grouped together. The source and target of those edges, source and target 1 and 3 will be connected together. So even though there may be several edges apart in the graph, they're connected in the same connected component. So this gives the coequalizer of X of S at X of T gives connected components of X. In other words, the sort of sets of vertices that are linked together. Different islands of vertices, right? And that's an incredibly powerful notion. And again, it has this notion of gluing. You'll notice you're gluing things together here. And we will find this again and again and again and again when we're dealing with these dual constructions. You see it with push out too, right? This gluing together of things. You glue things together that are mapped to by the same in a push out that have that same, common subcomponent. And so it is here. You have this gluing together notion that comes from the coequalizer. And it's extremely powerful that you could express something like connected components as a coequalizer here. So equalizers may seem at first, at glance to be kind of more directly familiar notions, right? It's like the subset of X that is mapped to the same value of Y. That kind of makes sense. The subset of X that X and Y agree where they map it. But
equalizer for graph, for the schema of graph,
the equalizer,
there's a subset of edges, yeah,
that are
have the same.
the same source and target. So in other words, reflexive edges, I guess, right? To be edges. So if we consider the equalizer of X of S
Less interesting.
and X of T,
Mhm.
this is going to be the subset of edges, because the equalizer will be over EQ, right? It's over here. It's a subset of edges. It's a monomorphism into edges, right? Right? Such that such that for each of them, their source and their target are the same. Same edge, the same vertex, which would mean reflexive edges, I think. All the edges that go to themselves, right? The source and the target of it has to be the same, which is, kind of useful, but maybe not like immediately practically, like you're maybe less likely to use that at a immediate practical goal, but sure, it could be useful. This is very useful, to be able to identify the connected components. And in CATLAB, this is a single line, right? You just say, take the coequalizer of these functions. So it'll take the coequalizer. And there's a lot of implicit computation going on there, but conceptually, it's a very powerful idea. So the coequalizer, I don't think we've ever discussed this actually in our group before. Equalizers, coequalizers as categorical gadgets, which we can use with our C sets and use with our computations. But they are incredibly versatile and powerful instruments, each with a feel that just whiffs of other constructions of its sorts, it just smells a little bit like push out, this idea of clumping things together, right? Yes, Meti.
If y